Thank you all for joining this presentation, and a bigger thank to Lacey for doing most of the heavy lifting part in terms of setting up the meeting and then, doing all the advertisement and everything. I'm Dr. Wolfrani, and today I'm going to talk about one of my research projects that I concluded recently, and it's about optimal integration of electric vehicles, which is going to be referred to as EVs from now on, and renewable distributed generation, or DGs, in distribution microgrids. This is part of the research that was funded by the UW Royalty Research Fund, or RRF. And first I'm gonna provide a background about the project. I'm going to talk about some of the challenges that the distribution grid faces with the integration of renewable DGs and EVs, and then I will go over the proposal, what we propose to address those challenges. I'm going to cover the methodology and go into some of the equations, the objective functions, the optimization that was done, for the project. I will then provide the case studies. What was used as the case study. It was basically a real distribution network that we use as the case study, and then I will provide the simulation results. And at the end, I'm going to conclude with some remarks about the project, and then I'm going to talk about some of the future work, or some of the work that has been in progress after this project was concluded. So without any further ado, let's get to the introduction part. The two economic sectors that are the largest contributors to the US greenhouse gas emissions are the transportation sector and the electricity generation sector. The transportation sector itself generates 29% of total US GHG, and that is followed by the electricity generation section, which generates about 25 to 26% of the total greenhouse gas emission in US. So as you can see, these two sectors combined generate more than half of the US GHG emissions. So now, if we could transition from the petroleum-based transportation method to those powered by electricity, and if we could also replace the fossil fuel generators by the renewable energy sources, we could significantly reduce the GHG emission in United States. And of course, there are some opportunities with this integration, and there are also some challenges associated with this integration. And I'm going to go, over those opportunities, over those challenges. I'm going to talk about those opportunities and challenges in more details, and I will show you, the consequences of not, taking care of those challenges or addressing those challenges, on a timely manner. So, about the opportunities. One of the obvious one is the environmental benefits that you would have because of the reduced GHG emissions. And there are some other benefits, which are basically the economic benefits. And one of the obvious one is the cost savings that you could have, because now you wouldn't have to pay all these, gas, to drive your car, and you would be also relying on, for example, wind speed and solar radiation to be able to generate wind power and solar power, and those resources are freely available. So, like what I said, it's an obvious kind of cost saving that you would have. There could be some other cost savings that are not as obvious as the first one that I mentioned, and one of them is renewable energy arbitrage. And by renewable energy arbitrage, I mean, you could basically take advantage of the lower market prices during the off-peak hours, and purchase the energy during those time, and then later on, when the the energy prices is higher, you could sell the energy back to the grid, and out of this transaction you could earn some revenues, and that's what I mean by the renewable energy arbitrage. And another opportunity that is the focal point of this research is the coordination between renewable DG and EV. So basically, instead of having the renewable distributed generators and the EVs operating individually towards their individual benefits, we would have a bilateral contract between the two and would have these two energy entities coordinating, by capturing the synergies that exist between the two energy entities. And by doing so, we would be able to increase the utilization of renewable resources. Because even though EVs are being touted as being emission-free, the way the electricity is generated to power the EVs could be not emission-free. So assume that you have a coal fire generator, or you have a gas fire generator that is generating electricity, and that electricity is being used to power your EV. So in that case, your net emission associated with your EV is not going to be zero, right? So that's why we propose to use the renewable energy generation to power our EVs. And by doing so, like what I said, we will be able to capture the synergies that exist between these energy entities. We will be able to increase the utilization of renewable resources, and we would also be able to alleviate some of the uncertainties that we have for the forecast of the renewable resources. Because again, talking about wind and solar generation, the amount of power that you're getting out of those generation is dependent on the wind speed and solar radiation that you're having. And even though there are some forecasts in terms of how much wind speed and solar radiation you're having, but there's always some error associated with those forecasts. And now, by this coordination, we would be trying to minimize these uncertainties, or minimize the penalties that would be associated with the forecast. Now, in terms of the challenges, one of the challenges that the distribution grids face is the additional loading because of the EV charging, right? So you would have all these EVs basically being operated within the distribution grid, and when they're charging, basically they're drawing current. So that's gonna translate into additional loading of the distribution grid. And then another challenge is that, because of this coordination that you're going to have between renewable DG and EV, and that's, like what I said, is one of the main things that we're doing for this project, you're going to have a continuous energy exchange between these two energy entities. So now, because of these continuous energy exchange, because of this additional loading, you may end up having some instances or some cases where the power flow exceeds the rating of the equipment, and that could result in equipment failure. And when we talk about equipment, we're talking about transformers, we're talking about generators, and these are all costly equipments, and their failure is going to result in a very costly kind of expense for us. Another challenge that the distribution grid is going to face is that the system losses is going to increase, and that's because of the additional loading that you're having within the distribution system. And because of that additional loading, because of the additional current that you're having, there's going to be additional voltage drop, and that's going to result in voltage deviation. So you're going to end up having voltages which are outside the acceptable standard range. So that's basically what it means by the voltage violations. And if all these challenges, the issues that I was just talking about, are not addressed properly, are not taken care of on a timely manner, then that could result in having some power outages across the distribution system. And just to give you guys some perspective, power outages cost US economy about $18 billion to $33 billion annually. So the consequence is going to be very, very costly. Now, here is what we propose to address some of these issues that I was just talking about. Our proposal was to develop a comprehensive optimization for integrating EVs and renewable DGs in distribution grids. And there are several aspects of this optimization that makes it comprehensive. The very first aspect or feature of this optimization is that it's a stochastic optimization. And by a stochastic optimization, what it means is that because of all the uncertain variables that you have within the distribution system, so you have all these wind, power generation, solar power generation, which would be dependent on the wind speed and solar radiation. And like what I said, those are all uncertain variables. So you also have the EVs whose driving patterns are kind of certain. So you need to basically characterize the system behavior, properly, and the only way to do it is to have a stochastic kind of optimization. So that's the very first feature of this optimization. And then we also, developed a coordination between the EVs and renewable DGs, and I'm going to talk about this in more details later on. But basically, we try to optimize the coordination, is what we did. And then after developing this coordination, we implemented this coordination on a distribution network, and then we evaluated the system from the operation perspective. We basically calculated all the bus voltages, we calculated the distribution system losses, and if we saw some sort of a voltage deviation or increased system losses, then we would have to come up with a strategy, with a method to address those challenges. And that's what we exactly did at the end of this kind of evaluation phase. Here, you can see the flow chart of the proposed method. As you can see, it's a hierarchical kind of optimization that we did. At the very top layer, where you have the red lines, is where we did the stochastic modeling of the random uncertainty. So basically, we gather historical renewable energy generation. We also gathered the data regarding the transportation behavior. And after that, we generated an autoregressive moving average, or ARMA model, for renewable generation. And also we developed a driving pattern for electric vehicle fleet. So instead of having to deal with each EV individually, we clustered the EV into fleets, and now within each fleet, we would be having like hundreds or thousands of EVs whose cumulative battery capacity would be considerable or would be significant to be used for whatever purpose that we were trying to use them for, right? And then after that, we applied Monte Carlo simulation to simulate the system states based on these ARMA models and the driving patterns that were developed earlier. So that concludes the very top layer of the optimization. In the middle layer, as you can see, the one that you have the blue lines for, we optimized the renewable DG and EV coordination. And what we did, we basically optimally charge and discharge EVs in coordination with renewable DGs to maximize their collective benefits. And again, I'm going to go in more details about this optimization and the equations that were involved in that optimization. And eventually, at the very last layer of the optimization, the one that you have the green dashed line for, is where we did the distribution grid operation and optimized that operation. So we implemented the coordination in a distribution network. We evaluated the distribution network in terms of the adverse effects that such coordination is going to have on the distribution grid operation. And then we developed a capacitor optimization to address those challenges or those issues. So now moving on to the methodology and the renewable DG modeling. Like what I said earlier, we use ARMA model. Here is the equation that was used for the ARMA modeling of renewable DG. There are so many parameters involved in this equation, which I'm not going to go into the details of it. But X, or what you're having here as X, is basically the wind speed time series. So basically, out of this ARMA model, we were able to model the wind speed. And after modeling the wind speed, then we use the wind speed in this equation to translate it or to convert it into the wind power. So as you can see, the P sub DG, which stands for the DG or distributed generator power output, you have three categories for that output. So the very first category where you have a zero output is where you're having the wind speed less than the cut-in wind speed and greater than the cut-out wind speed. So that's where you're not going to have any power out of your wind speed or wind turbine, sorry. And then in the middle equation, as you can see, those that is for the instances where the wind speed is between the cut-in wind speed and the rated wind speed, and that's how the power output of the wind turbine is calculated. And at the end, where the wind speed is between the rated wind speed and the cut-off wind speed, you're going to have the maximum power out of your wind turbine generator. And this is how we calculated the the wind power. In terms of the EV driving modeling, we use historical data of daily driving, and that's basically determines how many miles per hour each EV is being driven for. So we assume that our EVs are vehicle to grid or V2G enabled, meaning that they would be able to discharge their energy back to the grid. As you can see, there are two inequality kind of constraints involved in this modeling. So those are given by equation 3a and equation 3b. So the equation 3a says that the charging power of the EV must be smaller than the charging power rating. And equation 3b says that the discharging power of the EV should be also less than the discharging power rating. So we got to make sure that these two inequality constraints are satisfied whenever we're talking about EV charging and discharging. And at the end, we use clustering methods, and we group the EVs with the similar driving patterns into the same fleets. So now, like what I said earlier, instead of dealing with each individual EV, we would be dealing with EV fleets. So that's gonna create a much more significant battery capacity to work with, rather than working with individual battery capacity. So now at the end, of the first phase of the optimization, we use Monte Carlo simulation. And by doing the Monte Carlo simulation, we generated samples of the wind power, samples of the charging power and discharging power of the EV. And we made sure that we were generating enough samples so that we could reach the convergence. So that is a very important thing to consider whenever you're doing Monte Carlo simulation. And that's basically being done by taking the average of the values of the samples anytime that you're doing the simulation, and then you would do another iteration of the simulation. You would generate one more round of samples, and you would take the average value after doing one more round of iteration, and you would repeat the iteration. You would calculate the average value after every iteration, and then you would stop at a point where the average value is not going to change by adding one more iteration. So that's the point where you could say that now the convergence is satisfied, kind of, for the Monte Carlo simulation. So now moving on to the middle layer of the flowchart that I talked about earlier, and that was about the coordination between renewable DG and EV. And I need to give you guys a little bit of background before going into the details and the equations here. Basically, what we proposed here was to have a bilateral contract between the EVs and the renewable DGs. And the way that the power system operation works is that the renewable generators, so they would have all these forecasting methods, and based on the forecast of, let's say, solar radiation and the wind speed that they're getting, they're going to bid in the day-ahead market. And then based on the bid that they submitted, they would be scheduled to generate exact amount of power when the real time comes. So now the real time has come. So you're not getting enough wind speed that you were hoping for, that you were predicting for, and as a result you're generating less power than you were scheduled for. Or there could be some instances where the wind speed is blowing stronger than what you were predicting for, and you're getting some extra power than what you were scheduled for. The problem with this over generation or under generation cases is that you would be penalized for those cases, because you were supposed to deliver the exact amount of energy that you were scheduled for, and now you're going above or you're going under that exact amount. So you would be penalized as a DG, producer. So what we proposed, like what I said, was to have a bilateral contract between the renewable DG and the EV. So whenever there is over generation by the renewable DG, that excess amount of energy is going to be used to charge the EV batteries. And that energy can be purchased at a very low price, because otherwise it would have to be penalized or it would have to be dumped, right? And then later on, when there is under generation, you could use the V2G technology. You could basically discharge your EV battery, and you could compensate for the power deficit that you're dealing with. And that's usually occur at a higher market price, because that's usually during the energy deficit, right? Which usually happens, during the peak load hours. Anyhow, out of this transaction, basically by purchasing the energy at a lower price and then discharging it or selling it back at a higher price, you would be able to obtain some revenue, get some revenue for your EV. And that's basically formulated by equation number 5. If you look at equation number 5, you see two components. The very first component is the amount of energy that is being discharged times the market clearing price at that time. That's going to determine the how much money you're getting out of selling your energy. And then the second component of it is the money that you're paying to purchase the energy, right? And the difference between the two is going to determine the revenue that the EV drivers can get out of this transaction. And then when it comes to the DG, the renewable DGs, like what I said, one of the revenues that they could get is by reducing the penalties for renewable over and under generation. As a result, they would be able to increase the utilization of the renewable generation. And there are also some potential incentives, like the government incentives, such as production tax credit, that they could take advantage of. So the revenues for the DG is formulated in equation 6. And as you can see, there are two components. The first one is the PTC, which stands for the production tax credit. And then the second component, PEN, which stands for the penalty. And by having a negative value, basically, we would be trying to minimize this penalty, is what we're going to try to do. And here is the optimization that we're going to have for this coordination. So the objective function would be to maximize the collective revenue for EV and DG. As you can see, you have the addition of the two revenue components inside the objective function. And the goal would be to maximize the collective benefit or the collective revenue. Now, moving on to the very last layer of the optimization that I showed you guys in the flow chart. That was for the distribution grid operation optimization. And for that purpose, we developed a capacitor optimization. So basically what we did, we optimally sized and placed the capacitor across the distribution grid. And the objective was to minimize the loss of the system. And the loss, consists of three main components. So the very first component that you see in equation 8 within the objective function is the C sub loss. That's the cost associated with the distribution system losses. And then you have the second component of the loss, which would be associated with the capacitor bank. So for whatever number of capacitors that you're going to end up installing within the distribution system, you're going to have, the capital cost of the capacitor as well as the maintenance cost of the capacitor. And the sum of those two is what we're considering as the capacitor cost. And then the end, or the last component of the cost is the cost that you would have, for the voltage violation. So if there is a bus or there is a node across the distribution network whose voltage is falling outside the acceptable standard rate, there is going to be penalty. There's going to be a cost associated with that, a node or bus. And, for whatever number of buses is experiencing voltage deviation or voltage violation, we're going to have to add them up. And that's going to constitute the very last component of the cost. So Now, by this capacitor optimization method, we would try to minimize the sum of the cost that are provided in this equation. And of course, like any other optimization, our objective function is going to be subject to some equality and inequality constraint. I have listed some of those constraints here. So the very important one is the one that is given by equation 9, like what I said earlier. So your voltage is supposed to be within the acceptable standard range. So you would have a V minimum, you would have a V maximum, and you would expecting that your voltage of the buses of the system would be within that minimum maximum range. So now if you're not staying within that range, then you have this equation number 11, which is how much penalty you would have to incur because of being below the minimum lower rating kind of the voltage, and equation number 12, which determines the amount of penalty that you would have to incur for having your voltage above the maximum voltage. So now, moving on to the case study, we used a 13.8 kilovolt, 134 bus distribution network, which is a real distribution network. And what we did, we distributed 10 megawatt of wind capacity among 6 buses across this distribution grid: bus 11, bus 39, 52, 67, 84, and 103 are the buses that the 10 megawatt wind capacity was basically distributed amount. And then we also co-located the EV charging stations with the wind distributed generators. We integrated 484 EVs across the distribution system, and we ran 1,000 scenarios by Monte Carlo simulation, and that was the number of the scenarios that ensured we reached the convergence for our optimization. Anyway, this is the list of the capacitor banks that were used for our capacitor optimization method. This is a practical capacitor size. So we use 3 practical capacitor sizes: 600 kilovolt ampere reactive, 900 kilovolt ampere reactive, and 1200 kilovolt ampere reactive. And then the second column of this table, which shows the annual cost of these capacitor banks and the technology for all these capacitor banks, which were 3-phase Y connection. This graph here shows the energy cost in dollar per kilowatt hour over the 24-hour simulation period, and this was the cost that was used to calculate all those revenues that I was talking about, and also the cost components of the capacitor optimization and its objective function. Now, moving on to the simulation results. This is the results that we got out of the coordination optimization. As you can see, we ended up having 6 EV fillets, for the 484 EVs that were integrated into our, distribution grid. And this graph shows the discharging power of those 6 EV fleets. So there are some positive values, there are some negative values. As you can see in this graph, the positive values represent the charging status of the EV fleets, meaning that the EV fleets would be acting as loads during those instances or during those times. And there are some other values which are negative, and those are representing the discharging status of the EV fleets, meaning that the EV fleets are going to be operating or are going to be treating as a generator during those times. And now, by having the optimal charging and discharging power of the EV fleets like this, we were able to maximize the collective revenues for the 2 energy entities. And as you can see, these revenues are provided for the 6 buses that you had the EV fleets and the renewable DGs connected to. Now, moving on to the very last layer of the optimization that we did, as you recall, it was the distribution grid operation. So for that purpose, we used 3-phase unbalanced load flow analysis. And we ran that analysis after developing the coordination between the energy entities. So there's a lot of information provided in this slide. I'm not going to go into these information or all of them, but I can just let you know that what we did was to calculate the active power for each phase, for phase A, phase B, and phase C, the reactive power for the three phases, the current magnitude for the three phases, the losses of the system, the minimum voltage, and the maximum voltage. And the hour of interest here is going to be hour 19 because that's the hour where we had the heaviest loading condition. And as you can see from the numbers provided for hour 19, the distribution grid experienced 1,1257, excuse me, kilowatt in terms of the losses of the system. The minimum voltage was 0.865 and the maximum voltage was a 0.964 per unit. So now comparing the minimum and the maximum voltage with the Vmin and Vmax, which is the lower rating and the upper rating of the standard. So for the lower rating of the standard, we have a 0.95, and as you can see, the minimum voltage here, which is 0.865, which is way lower than the 0.95. So that's problematic, and we would have to address this problem, address this issue, right? Otherwise, you wouldn't be able to reliably and efficiently operate the power system. And in order to address that problem, we applied the capacitor optimization method. And here is the results of that optimization method. Again, the results are provided for 24 hours, but I'm just going to be focused on hour 19. And as you can see, the capacitor optimization resulted in having 5 1200 kilovolt ampere reactive capacitor banks installed at buses 27, 85, 113, 119, and 130. And as you can see from the table, we calculated the cost associated with the distribution system losses, the cost of voltage violation before installing the capacitor. And we also calculated the cost after the capacitor installed, and that cost was inclusive of the capacitor bank cost, right? And by comparing the two costs, we were able to provide the cost saving, to monetize how much saving the distribution grid would have as a result of this capacitor optimization. And as you can see from hour 19, after installing the capacitor, the system was having a cost saving of $282,124, which was huge. So now, having this capacitor installed across the distribution network, we ran another load flow analysis, which was an unbalanced three-phase load flow analysis. And here are the simulation results provided for that load flow analysis. Again, if you look at hour 19, you can see that now the distribution system losses is decreased from what it used to be 1,257 kilowatt to 906 kilowatt. Is a huge reduction in the distribution system losses. And you can also see that the minimum voltage is now increased to a 0.963 per unit from what it used to be 0.865 per unit. So that's an improvement in the voltage, the minimum voltage, and you also have an increase in the maximum voltage. As you can see, the maximum voltage is now 1.027 per unit compared to what it used to be before the optimization, which was a 0.964 per unit. So now if I go back to the post-optimization result, if I look at this minimum voltage and maximum voltage, you can see that the minimum and the maximum voltage is well within the 0.95 and 1.05 per unit, acceptable standard range. So here is to give you guys more context in terms of how the pre-optimization and post-optimization results are compared. This is the results for the hourly losses of the system across the 24-hour simulation period. The blue line shows the pre-optimization results. The red line shows the post-optimization result. And as you can see, the optimization resulted in reduced system losses consistently across the 24-hour simulation period. And then this graph compares the minimum voltages of the distribution grid before and after the optimization. The blue line shows the pre-optimization minimum voltages. The green line shows the post-optimization minimum voltages. And as you can see, by doing this optimization, we were able to make the minimum voltages closer to 1, right? Which is desired, because at the end of the day, you would like to have all of your voltages be as close as possible to 1 per unit. That's the desired kind of case or scenario. So here are some remarks about this project. A multi-objective optimization method was developed to integrate EVs and renewable DGs in distribution systems. And as you recall from that flow chart, so you had 2 layers of optimization. The middle layer, which was to basically have a coordination between the renewable DGs and EVs to maximize the collective revenues, and that is by having the 2 energy entities participating in electricity market, the renewable energy arbitrage that I talked about earlier. So it's more of a market-based coordination. And then at the lower level of the optimization, we did distribution grid operation optimization. So that's why I basically call this optimization or coordination more of an integrated market dash operation coordination optimization. So we were able to collect revenues for the 2 energy entities. We were able to just reduce the system losses. So basically, for the heaviest loading condition, the distribution grid experienced 28% reduction in system losses, which was significant. And we were also able to improve the voltage profile by reducing the voltage violation. Again, for the heaviest loading condition, that was of our interest, there was a 35% reduction in voltage violation, and as a result, we were able to provide a significant cost savings. So our method, basically we demonstrated that our method was applicable for relatively large distribution grid, the one that we tested, the 134 bus distribution grid, but it will be applicable to any other larger distribution grids. And this optimization, this method will facilitate widespread adoption of EVs and higher penetration for renewable DGs, and eventually it's going to advance the transition to more sustainable and eco-friendly energy systems. So this is the project that, like what I said, was concluded, and then has been some other work, that has been in progress. And what we've been trying to do was to come up with an alternative approach, basically to optimize the system, because the problem with the capacitor optimization is that you would have to put all this money to buy the capacitor and then to maintain the capacitor and operate the capacitor, right? And there could be also some transient stability issues associated with the capacitor operation. So now, in order to not have to deal with those problems, we are looking into an alternative kind of approach, which is called distribution system reconfiguration optimization. So basically what we were trying to do was to, close some of the normally open switches that you have within the distribution system, and also open some of the normally closed switches that exist within the distribution grid. And by doing that, reroute the flow of the power across the distribution network to be able to reduce the system losses. So if we do this in an optimal fashion, in an optimal manner, then we would be able to achieve the objective function and reduce the system losses, is what we've been trying to do, and has been the research in progress. And an advantage, associated with this method is that we now could basically consider the interconnection that the distribution network is going to have with the neighboring distribution system. So we would be able to capture the connected nature of the energy system this way, and the solution that we're going to come up with is going to be a more comprehensive kind of solution. Here is the list of the publications that this research project has culminated in. And with that, I'm opening up to any questions that you might have or any questions that you have put in the chat box, and I can answer those questions. But before doing that, I have Nawal, which I was one of the undergraduate research student, involved in this research here, and she could briefly, she's going to briefly talk about her research experience and the role that she played in this research. Nawal, please go ahead.
Hello, my name is Noel Hersey. I'm currently a senior here at the UW studying electrical engineering. And so this summer, I was able to work under the mentorship of Dr. Grafani here. And the goal of this summer was to identify existing weaknesses in these proposed methods. So considering the vital integrational challenges, as mentioned by Dr. Grafani here, which were the voltage deviations, the economic viability, and the power loss analysis. And most importantly, as well, the actual predictability of these renewable energy sources modeled by these stochastic variables. And so with this being said, there was a lot of strengths and weaknesses to all of these different proposed methods, but the framework that as well were able to thank you.